Hi everyone. So for this video, I'm going to be discussing ways in which we can solve a variety of the equations like we would have seen in algebra. So hopefully this video serves mostly as a review or a refresher from your algebra courses. If you have questions on any of the techniques or the families of equations we've discussed here, you can follow up with an email request in office hours and with tutoring. Okay. The first type of the family of equations for us to discuss is the basis for all other equations that we end up discussing. Those would be the linear type of equations. Okay. Linear equations are defined by having the variables all expressed to the first power, no variables multiplied by each other, and no variables in any denominator. An example of a linear equation in one variable, a general equation, would be ax plus b is equal to 0, where x is the variable, right? So we have x is to the power of 1. We don't have variables multiplied together. Now a and b are considered coefficients. Well, a is a coefficient, b can be a constant here, right? So we don't have variables multiplied together, and we don't have any variables in any denominators, right? Solving linear equations can be done by putting them in this form, ax plus b is equal to 0, and then solving for the variable x by using the addition and multiplication properties of equality that you learn in algebra class. Right? We can add any number to both sides. We can multiply any number by both sides of an equation, and it still balances. Right? We'll take a look at some examples of linear equations. Okay. The next family then, the next level up from there for us to discuss would be the quadratic family. Okay. The quadratic family can be expressed in its general form as ax squared plus bx plus c is equal to 0. So what defines it to be quadratic? Well, the degree of the equation is 2, and that's the highest power of the variable when it is a single variable equation, right? Again, x is the only variable in this equation when I've written it this way. A, b, and c are considered to be coefficients, and a is not equal to 0. Why is a not equal to 0? Well, if a was equal to 0, then this would just be bx plus c is equal to 0, and that would mean this would actually just be a linear equation, right? If a was equal to 0, this would have been linear. Okay. Some other types of equations. Okay. There's rational types of equations, and those are defined as ratios, but specifically ratios of polynomials. And polynomials are a larger family that include the linear and the quadratics and other higher powered polynomials as well, right? So we'll get more into that later in the course, more detail with polynomial. Okay, but basically a rational equation would be one where maybe you'd have like a polynomial function p of x divided by another polynomial function q of x, and that ratio is maybe equal to 0, for instance. And there are techniques that we can use in order to solve this. Okay, let's see. So p and q would specifically be polynomials, and q, that is q of x, we would not want that to equal 0, and that's an important concept. We don't want the denominator to equal 0, because then the expression on the left-hand side of this equation would be undefined, and a number that is undefined is not equal to any other number, right? So something that is undefined cannot be defined to equal 0, for example, right? So if the denominator is equal to 0, then the entire equation would have to be false automatically. Okay. What other types of equations do we have? Well, after rational, oftentimes we talk about the radical types of equations, and radicals can also be referred to as roots. Those are your square roots, cube roots, fourth roots, right? And more generally, right, so square root, a cube root, and more generally the nth roots, right? Okay, so example of a radical type of an equation, maybe something like the square root of 1 plus x plus the square root of 1 minus x is equal to 2. Okay. Okay, so we have at least one radical expression in this equation here. Okay, let's see, a couple other types for us to discuss as well. How about absolute value? That's one more, just one more to add to this. Absolute value equations. Now, the definition of absolute value is actually geometric in nature. We can interpret it as meaning distance from zero, or distance more generally, okay? But we're going to, in a single variable sense, where there's only one variable, we're going to think of it as distance from zero, okay? So an example of an absolute value equation, right? The absolute value is, the long vertical bars that enclose an expression, saying we're taking the absolute value of the expression. An example of an absolute value equation would be, let's say, the absolute value of 3x plus 5 is equal to 1. We'll take a look at that example. How do we solve something like that? Okay. And then one more thing that we want to take a look at here in this section, and that's going to be solving a formula, okay? Solving a formula for a variable. Okay? Now, a formula in mathematics, right, is an equation with more than one variable in it. So it is a way to relate more than one variable quantity, okay, to each other. Okay? So an example of a formula could be y equals mx plus b, right? The slope-intercept form of the equation of a line. And let's say we had that equation, and let's say that we wanted to solve it for x, right? Where we don't have any specific numbers or anything to plug in here, we just want to manipulate the formula to get x by itself. Okay, that would be an example of solving a formula for the variable x. Okay, what kind of an equation is this, by the way? If we say that m and b are coefficients, and x and y, if those are the variables, right? If this is a variable here and if this is a variable here, then we have a two-variable, right? We have a two-variable linear equation, okay? Make note of that, okay? This is still a linear equation in two variables. Oh, EQN, I'm just abbreviating equation right there in my own way. A linear equation in two variables is what we have here. Okay, where the two variables are x and y. And again, right? And again, we defined linear, a linear equation, okay, as having three defining characteristics. One, all the variables, okay, they are to the power of 1, so they have the exponent of 1. Okay? 2, okay, variables don't multiply by each other, alright? Okay, so let's say variables not multiplied together. Okay, variables are not multiplied together. And 3, you're not going to find a variable in any denominator. Okay, so we have no variable, can I abbreviate that var, V-A-R, no variable in any denominator. Okay, there we go. Now, linear equations and linear expressions form a basis for a lot of the geometric and other analytic techniques that we need in order to define the things that we're going to be doing in a calculus class. So it's important to understand the nature of linear equations and expressions, techniques for dealing with them, and then being able to use that information as a basis for dealing with other nonlinear forms of equations and expressions and geometries as well. A lot of calculus is dealing with linearizing things that are not linear. Okay, using lines to approximate things that are not lines, and building better and better approximations by using those lines. Okay, so we have lots of types of equations, okay, that we can solve. Okay, so let's try some out. Let's try some linear equations first. Let's see if I switch to another layer. Here we go. All right, let's try some linear examples. For a warm-up, let's start with one that's not too bad, right? 2 times the quantity 1 minus x equals 3 times the quantity 1 plus 2x, okay, plus 5. Okay. So this is linear. We can see that it's linear because the variable x is to the power of 1. There's no other variable to multiply it by, and there's no denominators with variables in them, right? It's possible to write all these numbers as fractions, but if we wrote any of these numbers as fractions, they'd be over 1. This is therefore a linear equation. Every linear equation in one variable can be manipulated and rewritten as ax plus b equals 0. That is a fact. If you know the family of the equation, if you know it is linear and it has only one variable, then there is a way to manipulate the equation to get it to look like it's in this form. And that puts you just 2 steps away from finding out what the variable x is actually equal to. It's very helpful to know from the start what family you're actually dealing with. Okay? So that then determines the types of techniques that you can therefore apply. Alright, so here's the techniques that we're going to apply here. Here's one thing I could do. I could distribute. We distribute the 2, distribute the 3. Alright, so we get 2 minus 2x on the left side. We get 3 plus 6x plus 5 on the right hand side. Alright, that was our distribute step. Okay, and now we can combine like terms, I'd like to say. So I'm going to do combine like terms, okay, CLT. Right. On the left hand side, I'll leave a 2 minus 2x, but on the right hand side, a 3 plus 5 is 8, 8 plus 6x. Right. Now I'm going to use what is called the addition property of equality. Right. The addition property of equality. That is where you can add anything to both sides of an equation and it's still a true equation. Right? So adding and subtracting is the same thing in mathematics. Subtracting would just be adding a negative amount. Okay? So the addition property of equality is the same as a subtraction property of equality. It's the same thing. Alright, so now we have 2 is equal to 8 plus 8x. Now we can subtract 8 from both sides, another addition property of equality going on there. So we have negative 6 is equal to 8x, and finally we can divide both sides by 8. Okay, we have an answer here. X is equal to negative 6 over 8. We should always be in the habit, unless told otherwise, we should be in the habit of reducing fractions to their simplest forms. In this case, we can, we can factor. It's a good word for us to use. We can factor the top and the bottom. I can write the top as negative 2 times 3. I can write the bottom as 2 times 4. And if you have a common factor on the top and the bottom, you can cancel the common factor, right? You may see that that's almost obvious here when it's just a 2 and a 2, but this technique, this concept is also true even if we were factoring expressions. So when we get more complicated looking expressions and equations to deal with, we can still use these concepts that we already understood. When they work with numbers, they are going to work with variables and variable expressions, right? So we have x is equal to negative 3/4. Okay. We have a potential solution. Now, how do we know if it's actually the solution? Okay, well, we can check this. We can check it, right, in the original equation, right? So for good measure, okay, 2 times 1 minus 3/4. We're going to ask, does that equal? I'm going to put a question mark above there, right? No, oh, I'm sorry. Right, I put negative 3/4 into here, right? So I should have 2 times 1 minus negative 3/4, right? Okay, so 1 minus a negative 3/4, right? Which you know what's going to happen next, right? I'm going to turn that into a positive. All right, equals 3 times 1 plus 2 times negative 3/4, okay, plus 5. By plugging this value into the equation, I'm not saying it's going to be true. I'm asking the question, is this actually true, right? So we're verifying whether the result is true. We have 2 times, let's see, 1 plus 3/4, okay, is that equal to 3 times the quantity, 1, let's see, we got 2 times negative 3/4. Well, that's going to be negative 6/4, right, and then plus 5, okay. What's 1 plus 3/4? Well, that's a 1 can be written as 4/4. 4/4 plus 3/4 is 7/4. So I get 2 times 7/4. is that equal to 3 times, let's see, 1 minus 6/4. That's 4/4 minus 6/4 is negative 2/4. Okay, or I could reduce that to negative 1/2. Do that as well. Okay, and then plus 5. 2 times 7/4, right, is going to be 7/2, right? We've got 3 times negative 1/2, right? So this is negative 3/2 plus 5. Okay, and 5 is the same as 10/2, right? So we have 7/2 is equal to negative 3/2 plus 10/2. The right-hand side is equal to 7/2. Okay, and the left-hand side is equal to 7/2. So we were asking the question, are the two sides equal under the supposition that x is negative 3/4? And we find that that is true. Right, so we've just reached a true statement. When you reach a true statement, right, when both sides are clearly the same as each other, okay, it says yes to whatever the question was we were asking. Mathematically, this is telling us the answer is yes to whatever question we asked. What was the question we were just asking up here? We were asking if this number was the correct solution to the equation we started with. We said, is this the correct number to solve the equation? And the answer we got was yes. Right? So we can interpret the mathematics that way. Here's another example. We'll see if it's linear or not. I got it. Okay, 2/3 y, okay, plus 1/2 times the quantity y minus 3, okay, is equal to y plus 1/4. Okay. All right. So this equation has fractions in it, right? Okay. Is it still linear? Well, there's only one variable. It's a single variable equation. The one variable is y. Every instance of y is to the power of 1. Okay? There's no y times another y or y times another variable. And although there are denominators, none of the denominators contain the variable y. So this equation meets the criteria. It is a linear equation. It is a single variable linear equation. So we can manipulate this equation so that it can be rewritten in the form a times y plus b is equal to 0, and then we would be able to solve it for y. We know that we can do that. And we can get there by just doing the same basic things we did in the last example. All right, using addition property of equality, for example, right, distributing, combining like terms, things like that. But we have one more feature here that we want to maybe clear out of the way, right? These fractions, okay? I like to, at the start of a problem that has fractions in it, I like to consider, do we want to in fact clear the fractions from the start? Consider that once the fractions are gone, once all the denominators are canceled out, we might have an even easier looking but equivalent linear equation to what we started with. We can clear the fractions if we can find the least common denominator, right? The least common denominator of 3, 2, and 4. The least common denominator of 3, 2, and 4, right? Okay, is the smallest number, right, that's divisible by 3, 2, and 4. That's going to be 12, right? If you did a factor tree on 12, right, right, 12 is what, 4 times 3, and 4 is 2 times 2, right? In the prime factors of the number 12, you can make up combinations that would give us any one of these denominators that we want, right? We got a 3, check, right? We got a 2, check. If we wanted a 4, we would take this 2 and this 2, check, right? So this is the least common multiple of the numbers 3, 2, and 4. Therefore is the least common denominator of our fractions. How are we going to use that? By the multiplication property of equality. That is to say, we can multiply both sides of an equation by any number we want, and it remains an equation. It stays balanced. So we'll multiply both sides by 12. So 12 times the 2/3 y plus 1/2 times y minus 3 equals 12 times y plus 1/4. You don't have to solve this equation this way, okay? But I like to introduce the technique here at the start and say, well, if you ever struggle with fractions, there, you could consider dealing with the fractions right from the start, maybe, right? Okay. What do we do now? Well, we're going to distribute the 12 to this term, and then to this term, and then over here we're going to multiply right this way. So we got 12 over 1, 12 over 1, right? So 12 over 1 times 2 over 3, well, the 12 and the 3 would, you can cancel the 3 with the 12, you get a 4, and 4 times 2 is 8, right? So the 3 is gone. So we are left with just an 8y. Next term, 12 times 1/2, well, 12 divided by 2 is 6, so we get a 6. Do we also multiply the 12 times the y minus 3? The answer to that is no, we do not, because we've already multiplied the 12 times the 1/2, and the result of that product is going to be multiplied by the y minus 3. Okay, so the 12 already got absorbed into this product as it stands. On the other side, we can take 12 divided by 4 is 3, so we have 3, but not 3y plus 1. In fact, 3 times the quantity y plus 1. We still have to distribute that 3. Notice we now have an equation that is still a linear equation, okay, but it no longer has any denominators other than 1, right? Okay, so we've removed that complication from it. This, in fact, is an equivalent equation to what we started with. That is to say that the solutions to this equation that we've created are exactly the same as the solutions to the equation we started with. What is different now, maybe it's in the eye of the beholder, is we have simplified the equation. We maybe have an easier equation to work with, although the solutions are exactly the same as the solutions to the original equation. Okay? Alright, so let's continue from here. 8y plus, let's do a distribution, 6y minus 18 is equal to 3y plus 3. Let's combine like terms now. Alright, we just did a distribution. Now we're going to combine like terms. 8y and 6y gives us a 14y, and a minus 18 is equal to 3y plus 3. Okay, and now we'll do the addition property of equality. We can subtract 3y, or that is add negative 3y to both sides, for instance. Okay, we get 11y. Right, I'll do a long line here for that. Okay, 11y minus 18 is equal to 3. Let's say I add 18 to both sides. Okay, we get 11y is equal to 21. All right, another instance of the addition property of equality there. Divide both sides by 11. Okay, so we get this number y is equal to 21 over 11. We know we can check the answer by plugging it back into the original equation, for example. Okay, let's move on to some quadratic examples. Okay. Quadratic equations. The standard form of a quadratic equation is ax squared plus bx plus c is equal to 0, where a is not equal to 0. The leading coefficient is not equal to 0. Right, so this would be the standard form of a quadratic equation of a single variable. Here the single variable is x. Some of the techniques that we have for solving quadratic equations, okay, include first factoring technique. That is, we can if we can factor the quadratic expression, we can then set each of the factors equal to 0. So that makes use of the zero product property, or the zero product rule. Okay, the zero product rule is if you have a product of 2 or more factors, okay, and that product is equal to 0, then one of the factors at least must be equal to 0, right? Either a is equal to 0 or b is equal to 0 in this example, right? This only works if the product is equal to 0. Hence, we need the standard form in order to apply factoring as a technique to solve a quadratic equation. In fact, to solve any polynomial equation. Okay, if we want to use factors, then we need the equation to be equal to 0. Okay, the next technique, okay, when factoring may not work, for example, we can move on to using the square root property, right? The square root property, that is, you can take the square root of both sides of the equation, okay, the square root property only applies in cases where b is equal to 0, right? So if you had something like ax squared is equal to c, right? Then you could divide both sides by a, and then you could say x is equal to plus or minus the square root of c over a, right? So the square root property really only applies in this case when b is specifically equal to 0, right? Let's say the linear coefficient is equal to 0. Okay, going a little further, we have a technique called completing the square, which has a geometric interpretation of a square. The technique known as completing the square we can apply to an expression such as ax squared plus bx by rewriting it as a times x squared plus b over a times x, okay? But then we would add in an extra term where that term would be half of this coefficient, that would be b over 2a, and then the quantity gets squared. And then in order to make this equivalent to the original expression, we have to subtract out the a times the b over 2a quantity squared. By doing that, we actually get a perfect square factor here. So we're going to get a times x plus b over 2a quantity squared minus this right here, which is going to be a b squared over 4a, for example. All right. Okay, it's a little complicated of a process there, and a bit to talk about there. We'll talk about it a bit more later in the course. It is a process whereby you could factor out the leading coefficient of the quadratic, okay, and then you take the remaining linear coefficient after the quadratic coefficient was factored out. This coefficient here, you divide it by 2 and then square it. It's a process called completing the square. Well, if we apply that process, that complicated process, to the standard form of the quadratic equation, we can actually then use the square root property. Okay, we can use the square root property then to isolate x. And when we do that, we end up with a formula that tells us what x will equal for every quadratic equation. And we call that the quadratic formula. Okay, the quadratic formula. And the quadratic formula, right, a result of completing the square on the standard form quadratic equation, will look like x equals negative b plus or minus the square root of b squared minus 4ac, and all of that will be over 2a. Right? This gives us a formula that will allow us to solve every quadratic equation we will ever see, every quadratic equation in a single variable that we would ever see, as long as a is not equal to 0. But we already said a would never equal 0, because if it did equal 0, then we would in fact have a linear equation. Okay, let's do a couple examples here whereby we'll focus on, in order to just solve the quadratic equations, let's do an example where we use factoring. Let's do an example where we use the quadratic formula. Okay, let's try a following example. Let's see. Solve by factoring. Okay, not every quadratic is going to be factorable. Every quadratic equation can be solved by the quadratic formula. Okay, but there's a significant price to pay there. There's a lot of cost in the amount of evaluations we may have to do. Factoring may be considerably less work if the quadratic is even factorable. And remember, the quadratic must be equal to 0 in order for factoring to be a technique that we can use for solving. Okay, let's try it on this one. 4x squared minus 4x minus 15 is equal to 0. How do we factor this? Okay, first, it's in standard form. Let's make note of that, right? We have an a is equal to 4, b is negative 4, and c is negative 15, and it is equal to 0. So it is in standard form, and it certainly is a quadratic. The highest power in the variable is 2. It's polynomial. Great. Okay, so in order to factor this, what we're going to do is, this is just my little way of organizing this. We're going to take the product of A and C, that is the AC product, the product of A times C. Well, in this case, A is 4 and C is negative 15, so the product of A and C would be negative 60. And then I'm going to take the negative 4, the value of B, and put that down here. Now we want to see, can we find two integers that multiply to equal negative 60, but the same two integers add up to negative 4? We can set up a table and start testing values, okay, as we wish, right? We want a product, okay, we want a product of negative 60, right, but we want a sum of negative 4. Maybe I'll say this is a sum, but this is a product, right? And we can start testing numbers. We can say, well, what's 1 times negative 60? But if we added those together, we would get negative 59, so that's not it. Well, maybe it's 2 times negative 30. But we add those together, we get negative 28, and that's not it. Maybe it's 3 times negative 20, right? I'm using this in a systematic approach, right? So eventually we're going to get it. And if we don't get a combination that works, we'll know that there isn't a combination that works also by doing this, rather than just guessing the numbers, right? Add these together, we get negative 17. That's not it. What about 4, right, times what? Times negative 15. We add those together, right, and get negative 11. Notice that by applying the numbers in this order, the way I've chosen here, we're getting closer and closer to the sum that we want, and the sum is negative 4. Okay? Let's see, how about 5 times negative 12? That would be negative 60. You add those together, you get negative 7. Well, that's not it. What about 6 times negative 10? Add those together, you get negative 4. Bingo, there we go. We got it, right? So we want a 6 and a negative 10, two integers that multiply to negative 60, but that add up to negative 4. How we can use that here algorithmically, one approach is we can split the middle term here, okay, the linear term, into two linear terms, each with these coefficients here, right? So I can rewrite the original quadratic as 4x squared plus 6x minus 10x minus 15 is equal to 0. And now we can do what's called factor by grouping. I can separate this into two groups of two terms, factor by grouping, and factor out the greatest common factor of each group. This group has a common factor of 2x. I can take that out, which leaves us with a 2x plus 3, right? If we were to redistribute the 2x, we would get back the 4x squared plus 6x, right? And this group over here, we can take out a negative 5, and guess what? That also is going to leave us with a 2x plus 3. Anytime you do factor by grouping, you're going to want to have the exact same binomial combination show up, or, it doesn't always have to be binomial, but in this case it will be. The same combination show up. If it's not the same combination in these parentheses, then the grouping didn't work, right? But here's the thing. If you find two integers that make this pattern work, a product and a sum that make it work, if you can find two integers that make that work, I guarantee that factoring by grouping is going to work as well, as long as you're dealing with a standard form quadratic. All right? So it's always going to work. Okay, now where do we go from here? Well, 2x plus 3 is a common binomial factor, so we take out the 2x plus 3, and that leaves behind a 2x and a minus 5, and then that equals 0. Okay? Now, if you have another way that you want to get to these two factors, that's totally fine. This approach is really robust. It's going to work on a wide variety of examples with a lot of different numbers and combinations. Okay. Now what do? We have a product equal to 0. We mentioned that earlier, right? We said, well, what does it mean if you have a product of two things equal to 0, which we do? We have 2x plus 3 times 2x minus 5 equals 0, right? Well, one of them at least must be equal to 0, right? So that means either 2x plus 3 is equal to 0, or 2x minus 5 is equal to 0. There we go. Okay, so that means 2x equals negative 3, or x equals negative 3 halves would be a potential solution here. And this means that 2x equals 5, or x equals 5 halves would be a potential solution. Potential because we could still check them. We should still check these in the original equation to be sure. okay, or otherwise verify that they are correct. And in this case, you can go and check them and see whether they are in fact correct for this equation. Okay? All right, what did we do? By factoring, we could say we were able to take the standard form quadratic and we kind of busted it down into pieces where we ended up creating not one but two. What kinds of equations are these? We created two independent linear equations, right? So we took something that was nonlinear, right, a quadratic, which is nonlinear, and we applied a technique that ended up reducing it into a combination of linear things, right? And then we could just apply to solve each of these equations. It was just a matter of solving basic linear equations at that point, okay? So remember that that's, the big picture of what we did here, right? We took something that was more complicated than linear and found a path to make it look like it was linear, right? Okay, let's try an example. We did quadratic formula. Why didn't we just do quadratic formula in this one? Well, because the instructions said factoring. That's why. Could we have done the quadratic formula? Yes, absolutely. In fact, another key that could be used to determine whether you could do quadratic formula or factoring, right, if either is a possibility, is by looking at this little expression in here, inside of the radical. All right, or this is called the radicand. It's the expression inside the radical, and we have a special name for this one in the quadratic formula, and that's called the discriminant. All right, okay, the discriminant. And if the discriminant is a perfect square, notice then we're going to take the square root of that discriminant, okay, which is going to allow us to simplify this without a radical anymore, right? Because the square root of a perfect square, right, is going to be able to eliminate that radical. Okay, so we can see that, okay, if we were to look at the discriminant of this of this quadratic right here, I expect to see a perfect square. Okay, a perfect square. The discriminant here, okay, would be, let's see, b squared minus 4ac. Okay, I don't have much room here really to do this right now, right? So I might have to clear some space. Negative 4 squared minus 4 times 4 times negative 15, right? That would be the discriminant for this quadratic, right? So I took b squared, okay, minus 4 times a, right, times c. And I'm saying that this is going to be a perfect square because the thing factored, okay? That's what the theory suggests, right? So we have, what, a 16, and then this is right, 4 times 4 is, or 4 times 15, right, is 60, and 60 times 4 is what, 240, right? So 240 and 16 is 256, and 256 is a perfect square. It's 16 times 16. So the square root of 256 is 16. This is not going to be left with a radical. We're going to get nice rational numbers as our solutions here. That's just combinations of integers, okay? It's a suggestion that it's going to factor. Okay, we'll be returning back to talking about things like the discriminant, and definitely analyzing quadratics more later in the course. Okay, but now I want to take a look at an example whereby we solve by using the quadratic formula itself. Let's practice using the formula. So I'll go to a new layer here. Okay. Solve. Let's just say solve the quadratic. 3x squared minus 6x minus 1 equals 0. Now let's just say we wanted to see if it factored. If we wanted to see if it factored, we could check the AC product, which is 3 times negative 1 is negative 3, and the value of b is negative 6. We could ask the question, are there two integers that multiply to equal negative 3, but that add up to equal negative 6? And it wouldn't take long for us to find out. There's not many combinations that multiply to negative 3, but none of them add up to negative 6. So factoring is off the table, right? This does not factor. We can still solve the equation, though, if it has solutions by using the quadratic, real solutions, that is, by using the quadratic formula. Okay. We may remember that the square root of a negative number gives us an imaginary number, and that leads us to complex numbers. Some quadratics can have complex solutions. We are dealing exclusively with real numbers now, unless told otherwise. So when we're asked to solve something, solve an equation or an inequality, for example, okay, we should assume we're dealing with real numbers, unless told otherwise. Okay, anyway, factoring won't work on this equation, but we can use the quadratic formula. Quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac over 2a. Okay. If you struggle with remembering the quadratic formula, I suggest that you write it down at the start of any problem where you're going to be using it. So the more you write it down, maybe, becomes maybe easier to recall as well. Start plugging values in. What is b? B is negative 6, right? B is equal to negative 6. So the opposite of b would be positive 6, right? So we have x equals 6 plus or minus the square root of, now we got b squared. Remember, b was negative 6, and we are going to square it, okay? But I want to make note, we are putting parentheses around this negative 6 because we are multiplying negative 6 times negative 6. If the parentheses weren't there, this would equal a negative number, okay? If we, after we squared it, it would actually be negative 6, right? If we write negative 6 squared, that is not the same as writing negative 6 quantity squared, right? Those are not going to equal the same as each other. Your calculator will agree with me there. You can check on your calculator to see. Alright, so we got negative 6 quantity squared, and then minus 4 times a, which is equal to 3, times c, which is negative 1. Right, and that all is divided by 2 times 3, because 3 is equal to a. Now we want to go ahead and simplify this as much as we can. Okay, order of operations, okay, on the inside of the radical. So we have 6 plus or minus the square root of, it's going to be 36. We got a negative times negative is positive, 4 times 3 is 12, so I'm going to do a plus 12, and this is over 6, okay? So x is equal to 6 plus or minus the square root of 48 divided by 6. Okay, now how to properly cancel the 6 here? Can't just cancel this 6 with this 6 and call it a day, because of this plus minus here, right, this square root of 48 is also over the 6. So I would suggest that we write it as 6 over 6 plus or minus the square root of 48 over 6. That could be one way to avoid the mistake of just canceling these and leaving this alone. Okay, separate them. Now this can reduce to 1, okay? That can reduce to just 1, but this we have to do a little more playing around with. We want to simplify the radical, so we'll find a perfect square factor of 48, right? The perfect squares include, what, 4 is a perfect square, 9 is a perfect square, 16 is a perfect square. Well, 48 has a factor of 16. In fact, it's 16 times 3. Okay, so 16 times 3 is 48, 16 is a perfect square. Now we can simplify the radical a little further. The square root of 16 is 4. The square root of 3, okay, square root of 3 is irrational. Okay, so that doesn't reduce any further. So that 3 stays inside of that square root, and there's a 6 on the bottom. We now have a fraction that can be reduced, and as we said earlier, as I mentioned earlier, okay, whenever you have a fraction as the answer to a problem, unless told otherwise, you're going to want to simplify it to its most simplified form, or its lowest terms. So we can factor out a 2 from the top and a 2 from the bottom. So I have 1 plus or minus 2 root 3 over 3. Okay, we have 2 solutions here. Okay, we have 2 irrational solutions here. Okay, we have 2 irrational solutions. Okay, they are real numbers. Okay, they are real numbers. But they're irrational. What is irrational? Right? Remember that a rational number, we talked about what a rational expression was briefly earlier. A rational number, okay, is the ratio of 2 integers. Okay, the ratio of two integers. And integers are the numbers like 0, plus minus 1, plus minus 2, plus minus 3. The only exception to this rational number definition is the denominator in the ratio can't be 0. Right? An irrational number is a number that cannot be expressed as a ratio of two integers. The square root of 3 is an example of an irrational number, making this entire value here, or both of these values, we should say, right? We have 1 plus 2 root 3 over 3. We have 1 minus 2 root 3 over 3. Those two values right there, okay? Those are each irrational, okay? Irrational values. Okay. All right. Let's try another kind of an equation here. Okay, let's try a rational type of an equation. Okay, let's see. I have one here. Let's see, 3 over x plus 1, okay, minus 1/2 equals 1 over 3x plus 3. Okay, this is a rational equation. It is a ratio. The expressions are built up out of ratios of polynomials. In this case, we see that there are linear expressions in the denominators. So this equation is not a linear equation because we have variables in the denominator, right? Okay, but it is a rational equation because we have polynomials in both numerator and denominator. Anyway. So it's an equation that has fractions, but there can be variables in the denominator, right? It's a rational equation for right now, okay? But really, these variables have to be to whole number powers in order for it to be rational. More about that later in the course. We'll revisit it again. How to solve this. The big picture here, as I see it, is we are dealing with fractions. I mean, we don't know what x equals yet. We know what it can't be, maybe, right? We know that x cannot be -1, right? Because if it was, then the whole statement would be meaningless. The denominator can't be 0. Okay, but we don't know what x does equal. But x is a number, and once x is determined to be some number or a set of numbers, okay, then these are really all fractions. What do we do to deal with equations involving fractions? Well, I suggested earlier we could multiply by the LCD. And we need the LCD of x plus 1, 2, and 3x plus 3. Notice that 3x plus 3 itself factors, right? 3x plus 3 does factor as a 3 and x plus 1, right? 3 times x plus 1. Okay, so the LCD has to have a factor of 3, a factor of x plus 1, and a factor of 2. Okay, so the LCD has to have a factor of 3, a factor of x plus 1, and a factor of 2. In other words, the LCD is going to be 6 times x plus 1. Alright? So, see what happens if we multiply both sides by 6 times x plus 1, the LCD. Okay, we have 3 over x plus 1 minus 1/2. On the right-hand side, we have, 6 times x plus 1, which is going to get multiplied by 1 over 3x plus 3, and I'm going to factor the 3 times x plus 3 into a 3 times the quantity x plus 1 for simplicity here. Now we can start distributing to the terms. 6x plus 1 times 3 over x plus 1, we get to cancel the x plus 1s with each other there. That leaves us 6 times 3, which gives us 18 from the first multiplication. 6 times x plus 1 times -1/2, we can cancel the 2 with the 6 to leave us with a 3, but the x plus 1 stays. The other thing that stays is the minus. So we still have a minus sign. The 6 divided by 2 gives us a 3, and the x plus 1 is still left. Alright, still remains. Okay, on the right-hand side, we can cancel the x plus 1s with each other, and we can cancel this 3 and with 6 to turn that into a 2, right? So the right-hand side is simply going to be the number 2. Now we have transformed the equation. It was originally a rational equation We used the LCD, right, which was quite challenging maybe, but we used the LCD in order to clear the fractions, and what we're left with is this equation. And this equation is of what type do we recognize? We have one variable, and that is to the power of 1, and it's not in any denominator. This is now a linear equation that we have formed. All right? And we know how to solve every linear equation, right? So we've already talked about that. This linear equation can be written in the form ax plus b is equal to 0. And if we can write it in that form, we know we're just 2 steps away from solving it. So this is certainly solvable. Okay. Now this is an equivalent equation to this one up here if we consider that they must both share the same domain or the same restrictions. The original equation, we noted that x could not be -1. It must also be true that this equation, even if it doesn't look like it, that in this equation x cannot equal -1, even though there's no denominator here. For this equation to be equivalent to this equation, we should consider that they must have the same restrictions, the same domain as each other. Okay? Suppose if we were to solve this equation, and this can happen in some examples, if we were to solve this linear equation and get exactly the number that we didn't want back here, okay, we would want to be sure to check our solutions, either by plugging the number back into the original equation up here where it could have caused a problem, or by checking it against the domain restriction. All right? If we get as a solution to this equation, if we happened to get exactly what we didn't want, we would label that solution as an extraneous solution. It would not be a solution. Okay? So we can apply all the proper technique, okay, all the proper mathematical technique, and still end up with a solution that is in fact extraneous or not a solution. Let's see what happens here. Distribute the -3, I get a -3x and a -3, and then equal to 2. 18 minus 3 is 15. 15 minus 3x is equal to 2. -3x is equal to -13, subtracting 15 from both sides. Divide by -3. X is equal to 13 over 3. That's not equal to, right? That is certainly not equal to -1, so it's not extraneous. But in order to verify that it's actually the solution to the equation, we really should go about plugging it back in, not to the linear form. We should really be plugging it back in the original equation, okay, and simplifying it from there, okay? The solution here, I can tell you, is correct. I've already checked it earlier, okay? But you want to verify it. You know, it's good practice with the arithmetic to plug it in here and see that you can do that, okay? So that's an example of a rational equation. Okay, we'll look at more of those later in the course as well. Okay, how about a radical equation? Right, earlier in this presentation I wrote down the square root of 1 plus x plus the square root of 1 minus x is equal to 2. It's a radical equation that has radicals in it, in this case the square root. Okay? Now the technique, a technique that may work dealing with radicals, and it will work for these examples that, that we'll be seeing for right now, the technique that we have that will work. Okay, I put it in just a couple steps. First, isolate a radical. Pick one of the roots, one of the radical expressions, and isolate it on one side of the equal sign or the other. And second, eliminate the radical, okay, by raising it to an appropriate power. But you must do it in that order. We're tempted here to square the square root, which is what we want to do to eliminate it. But if we did it before isolation, we would not be allowed to distribute the square. You cannot square this, and square this, right? Squaring is not an operation that distributes, okay? If we were to square, we would have to square the whole side, and that requires that we actually FOIL out the entire side, and it's not going to give us the correct solutions unless we we go about doing that. It's going to create a mess out of this equation. Okay, let's try this instead. Okay, I'm going to isolate one of the I'm going to isolate this square root right here. Okay, do that by moving the other one to the other side of the equation. So root 1 plus x equals 2 minus root 1 minus x. Okay, now eliminate this square root by squaring both sides. Okay, gonna square this, but now we're gonna have to square the entire side over here. All right, can't distribute the square. We have to FOIL this out now. But on the left-hand side, we will be left with just a 1 plus x. On the right-hand side, right, we are figuring out what is 2 minus root 1 minus x times 2 minus root 1 minus x. Okay, and we are FOILing that out. 2 times 2 gives us a 4. We get a minus 2 times root 1 minus x, but then we get another minus 2 times root 1 minus x, so for a minus 4 root 1 minus x. And then we get minus times minus is a plus, and root 1 minus x times root 1 minus x is just, well, 1 minus x. Okay? Alright, now we can reassess. What kind of an equation do we have now? This side looks linear, but we still have a radical in there. So the equation is still radical. What technique can we apply? We can try it again. Isolate the radical, eliminate the radical again. Okay, so let's get it isolated. How can we isolate? Let's start moving the terms to the other side of the equation. I'm going to combine these. 4 and a plus 1. I'm going to combine those with each other. That gives us a 5. Right, and then we have minus 4 root 1 minus x, and then minus x. Okay, continuing with isolation. Let's see. I'm going to add x to both sides. I'm also going to subtract 5 from both sides. We're going to start combining these steps now. 1 minus 5 is negative 4. X plus x is 2x. And on the right-hand side, right, we've canceled this, we've canceled this. We are left with negative 4 root 1 minus x. The term with the radical in it is now isolated. Okay, I could mention that. It is isolated now. So now we can go ahead and we can eliminate. Okay, right? We have isolated the radical term at this point on this side of the equation. Right? So now we can eliminate it by squaring both sides. Okay? Okay, so I'm going to square this side and I'm going to square this side as well. Okay? Alright, this serves the purpose on the right-hand side. What we're going to do is we're going to square the negative 4, which gives us a 16, and then we're going to square the root 1 minus x, which gives us just 1 minus x. On the left-hand side, we're going to FOIL this out. Okay? We're going to have negative 4 plus 2x times negative 4 plus 2x, right? Okay. Negative 4 plus 2x, negative 4 plus 2x. FOIL that out. So we get a 16, and then we get a minus 8x, but another minus 8x, so a minus 16x. And finally, 2x times 2x is 4x squared. Okay? We can distribute the 16 as well. You know, can we see what kind of an equation we're going to get now? 16 minus 16x. What kind of an equation does this now look like? We have the highest power is 2. We have no more radicals left. There's no denominators with any variables. We now have a quadratic equation. So we've transformed our radical equation into a quadratic equation. And that means that we can rewrite it as an ax squared plus bx plus c is equal to 0 if need be. And then we can apply the quadratic formula, or maybe even a factoring technique. In fact, maybe even the square root property. Let's see what happens as we start to simplify this into its standard form. Okay, so of all the x squared terms here, this is the only one, right? We have a 4x squared. What would be the bx? Well, negative 16x here and a negative 16x here as well. If we were to add 16x to both sides, they would cancel each other out. So it turns out b is equal to 0, right? And then we've got a 16 and a 16. So what is c? Well, we can subtract 16 from both sides. They cancel each other out. We have 4x squared is equal to 0, right? That means x squared is equal to 0, because we can divide both sides by 4 to get that. And of course then x is equal to 0, right? 0 is the only number that is neither positive nor negative, right? If we said plus or minus the square root of 0, right, we still would have only one solution being 0. All that work to find out that x was equal to 0. For this example, yes, that was actually so. All right, let's take a look at the original equation. If x was equal to 0, right, if x was in fact equal to 0, we would have the square root of 1 plus the square root of 1, which would equal 2. And that's correct. But we also know that it's the only solution to the equation in this case. Okay? Nonlinear equations may have more than one solution to them, okay, in general. So even if we can spot one off the bat, if we think that we know what one of the numbers is that solves a nonlinear equation, we should also bear in mind there's the possibility there could be more solutions depending on the characteristics of the equation. Okay, let's add a new layer here. Okay. Okay. Alright, we did linear equations, quadratic, rational, radical. You can see as the equations get more complex, as the families get more complex, the techniques that we apply have the potential of really transforming the equations themselves into the earlier forms. We turned a radical equation into a quadratic. Earlier we turned a rational equation into a linear equation. We turned the quadratic into two linear equations. At the heart of it, we need to be able to solve linear equations really well. We know how to solve every linear equation we'll ever encounter already. We need to know how to solve quadratic equations. By the quadratic formula, we know how to solve every quadratic equation we will ever see. By applying techniques to these more complex families, okay, to make them look like quadratic and linear equations, right? This allows us to solve even more complex problems, okay, by simplifying the problems. Okay, now try the absolute value one. Okay, absolute value of 3x plus 5 is equal to 1. Definition of absolute value, distance from 0. Okay. All right. Absolute value of 3x plus 5 is equal, sorry, it's not so clean, is it? Okay, 3x plus 5 is equal to 1. There you go. So what we're saying is geometrically is that the expression 3x plus 5 lives 1 unit away from 0, right? That 1 is the distance from 0. On a number line, it's on a number line because we have only one variable here, the variable x. So I'm going to draw a number line here, the real number line. Okay, the real number line. Okay, this is 0. That's home, right? This is home for 3x plus 5. Home. 3x plus 5 lives exactly 1 unit away from 0. That means either 3x plus 5 is at, okay, I'm saying it lives at home, right? But it is currently at either the location positive 1 or it is at the location negative 1. That way 3x plus 5 is exactly 1 unit away from 0. That is to say, let's transform this this geometric interpretation, right, back into a symbolic one. Either 3x plus 5 is equal to negative 1 or 3x plus 5 is equal to positive 1. And what kinds of equations do we have here? We have two linear equations now that we can solve. Okay? And we know how to solve every linear equation we will ever see, so we know what to do. Let's subtract 5 from both sides in this case. I subtract 5 from both sides. 3x equals negative 6. Over here, same thing. Subtract 5 from both sides, but we'll get 3x equals negative 4. Divide by 3, divide by 3. We get x equals negative 2. And over here, divide by 3, divide by 3. We get x equals negative 4 thirds. Okay, two potential solutions. We can see if they're correct by plugging them in. Okay, absolute value of 3x plus 5, right? Let's check real quick. The absolute value of, right, 3x plus 5, right? So 3 times negative 2 plus 5. Does that equal 1? And for checking this one, the absolute value of 3 times negative 4 thirds plus 5, does that equal 1? We'll check these two. By order of operations, starting on the inside of the absolute value bars, right? 3 times negative 2 is negative 6, and then we'll add 5. Okay? Negative 6 plus 5 is negative 1, and the absolute value of negative 1 does in fact equal 1, so that's confirmed. X equals negative 2 is a solution. The other one, 3 times negative 4 thirds, that's just negative 4, so we have the absolute value of negative 4 plus 5. Does that equal 1? Negative 4 plus 5 is 1, and the absolute value of 1 is 1, so that's confirmed as well. Okay, so the technique for dealing with absolute value when you have a single variable is to interpret absolute value geometrically as distance from 0 on the number line. When it's an equation, we're saying that that distance is exactly equal to the number on the other side, right? The distance is exactly equal to 1. When we start dealing with inequalities, like less than and greater than, we'll be still using the notion of distance, but we'll be saying the distance is less than, let's say, 1, or more than 1, which will give us intervals on which we can find solutions when we talk about inequalities in the next section. Okay? There's one more type of exercise to go over, and that is solving a formula for a variable. Okay? Solving a formula for a variable. So, for example, solve the formula y equals mx plus b for the variable x. It's a linear equation. We can consider that x is the important variable to us here. We can solve this linear equation for x by isolating x. Okay? Simply want to isolate the variable of interest, okay? The variable of interest, which in this case, the variable of interest happens to be x, because we were told to solve for it. Okay, so to get x by itself, we can start by isolating the term, the mx term, and subtract b from both sides. Y minus b equals m times x. Then divide both sides by m. That way, x is left all by itself on one side of the equation, and there are no instances of x on the other side of the equation. Then we know that we have solved for x. X equals the quantity y minus b divided by m. Okay. I'll try in one more example here and finish up. Solving a formula for a variable. We're going to take a formula from electrical engineering. So if you have a circuit, if you have a parallel circuit, okay, a wire, okay, current is flowing through, and the wire, the material determines amongst other things, determines the amount of resistance that there is to the flow of electrons to the circuit. So if you have a certain amount of resistance in each of these wires, and they may not be the same amount of resistance, so let's say R1 is the resistance here and R2 is the resistance here, right? So you imagine flow of electrons like a flow of water, and it's splitting into two different conduits here, okay, and there's a certain amount of pressure here, or blockage resistance here, a certain amount of resistance here. Well, what is the total amount of resistance that we're going to get, okay, in the output of this circuit here, okay? And that's found out by the formula, the reciprocal of the total resistance, right? 1 over R is equal to 1 over R1 plus 1 over R2. Let's solve, okay? Let's solve this formula here, okay, for, let's say, R1. Solve it for R1, okay? So the variable of interest now is R1, and that variable is located in the denominator here. So this looks mostly like a rational type of a thing, right? It sort of looks like a rational kind of an equation as a result of that, okay? The technique that we had said we could do before, that was one thing we said we could do, is use the LCD. In this case, R1, and R2 could potentially be different quantities than each other. Okay, none of them would equal 0. Okay, but they could be different values than each other. So the LCD would be the product of the three, R times R1 times R2. And we can use that LCD the same as we did earlier. We could multiply both sides of the equation by that LCD. R times R1 times R2. 1 over R on the left, and then R times R1 times R2 times 1 over R1 plus 1 over R2 on the right. Okay? On the left-hand side, we can cancel R with R, which leaves us with R1 times R2. On the right-hand side, okay, we can distribute. For the first multiplication, we cancel R1s. That leaves us with R, R2. And in the second multiplication, we cancel R2s, which leaves us with a plus R times R1. Okay. What kind of equation do we have now? If R1 is the only variable of interest to us, is the only variable, right? In other words, if R2 and R are not considered to be variable right now, then in fact we have, well, it's R1 to the first power, R1 to the first power. In fact, this is a linear, right? This is a linear type of an equation here, okay? Just imagine that R2 and R are just numbers that we don't know, but not varying. And R1 is the one that we're actually interested in to be the variable, okay? So it is linear in that sense, okay? How do we get R1 by itself? Okay, notice we have an R1 over here. We have another R1 over here, but we do not have an R1 on this term right here. Let's collect the R1 terms together on one side of the equation. R1 times R2 minus R times R1, okay, equals R times R2. Now that we've collected R1s on one side of the equation, we can factor out the R1 because it is the greatest common factor, okay, the greatest common factor of this expression over here. So we remove the R1 as a factor, right? Okay, we are factoring out the R1 as the GCF. All right, we get R1 times the quantity, R2 minus R, and then that is equal to R times R2, and then finally we can isolate the one remaining R1 by dividing both sides by this R2 minus R. R1 equals R times R2 over R2 minus R. Okay, so we have solved the formula for R1, given that R1 is isolated on one side of the equation, right? And on the other side, we see no more R1s remaining, right? The only R1 we have is over here. So you have a set of homework problems, right? But also you have, this video here, lecture, to refer to in the future as well, as we continue to talk about taking more complex problems, breaking them down, trying to make them more simplified. Our ultimate goal in a lot of cases is to linearize problems that are nonlinear, okay? Because of all the types of equations, of all the families we could hope to be solving, okay, the linear ones are the ones that are the least problematic to us, okay? All right, have a good day, trying out the new homework, okay? Let me know if there's any questions or concerns, okay? And I will talk to you again sometime soon. All right, take care.